In this video, we're talking about parts 1 and 2, so this is either a review from class, or this is because you were absent you're watching this video. Either way, welcome. Let's get started. So, nuclear chemistry, we're looking at our nucleus, and we're getting a little review of our atomic structure to really understand what that means. So first, you're setting up your notebook. You want to title these pages Nuclear Chem Notes 1, 2, 3, etc., and make sure that you have your left-hand column set up to add your titles, etc. later on. And then you only need a summary section at the very last page. This set of notes ended up taking me 4 pages. And so my summary fit on my 4th page. That's where that was. And of course, yours can be different. Take as many notes as you need. All of the content of these slides are included in our Unit 2 assessments. Items that are highlighted or underlined are obviously especially more important, but take as many as you need. And then there's a copy of my notes. When I went through these and took some notes just to model it for you, there's a copy of those that can be found in this presentation, linked in the NEO assignment as well. This is slide 3. So our first part is atomic structure review. So we're going to talk a little bit about those subatomic particles that we took some notes on last week. And we're also going to start talking about isotopes and how we can find that information on the periodic table. So how can we discuss atoms without having to draw them? So we want to start on how to write out the notation for these without having to try to draw the atoms or model the atoms every time. As a review, we have 3 subatomic particles contained within an atom. There are 3 different types of particles within an atom. Protons are positive, neutrons are neutral, both of those are in the nucleus, and our negative electrons are found outside of the nucleus, separated from each other. Each whole atom can be identified by its unique number of protons. But these subatomic particles are present in different numbers in all atoms in the universe. That unique number of protons is important because it's the way that we identify an element. The different number of protons is a new element. Every possible atom of carbon will always have 6 protons in its nucleus. It might have a different number of electrons, it might have a different number of neutrons, but by definition, carbon will always have 6 protons. That proton is the only number that can never change. And we use our periodic table to find out some of that information. Atomic mass, so the mass of an atom, is measured in AMU, or what are called atomic mass units. And 1 AMU is the weight of 1 proton or 1 neutron. They have the same mass. An atom's electrons are so tiny that even the mass of them isn't enough to affect the overall mass of the atom. We call that negligible. Negligible means it's too small to really matter. So our atomic mass is just protons and neutrons. And you should definitely copy this table into your notes if you haven't already. Our abbreviation for proton is P with a superscript plus or just a plus sign. Charge is +1. Mass is 1 AMU found in the nucleus along with the neutron. Neutrons have no charge. We typically abbreviate those with a little n. And then electrons are e to the minus, or just a minus, and they are found outside of the nucleus with a negligible mass, too small to count. So at this point, you want your periodic table available for you to be able to reference. And it's linked in here. It's also already in the chemistry packet, so either print it or use the one from the packet you picked up. And what we're using the periodic table for in this lecture is to find the atomic numbers and symbols for elements. So you can see this here, which I recommend you copy into your notebook. This little key will help us find some information. So if we know an atom has an atomic number of 8, we can look it up on the periodic table and identify it as oxygen, chemical symbol, capital O. This is what that periodic table looks like. So if you need to copy the key into it, you can do that if you're using the sample from the packet. Otherwise, we can use this periodic table to identify our elements. Let's start with atomic number. Atomic number is our number of protons, and we already know from earlier the number of protons is what gives something its identity. You can find this on the periodic table. We can see here it's the whole number, usually at the top of the periodic square. And this is the amount of protons in the nucleus, and it gives it its identity. So in this case, we're seeing oxygen as our example. Oxygen has an atomic number of 8. That means any atom in the entire universe that has 8 protons is always oxygen. And this is the only characteristic that is guaranteed to be the same for atoms of the same element. Like I mentioned earlier, electrons can change, neutrons can change. Atomic number, which is the number of protons, cannot change. Mass number. Now this is very commonly mistaken for being on the periodic table. You cannot find mass number on the periodic table. You'll notice on the key it says what's called atomic mass. That is not the same thing. Mass must be given. We can't just imagine what the number of neutrons is, and we can't use that weird decimal number from the periodic table. We have to be given the mass number. And conveniently, elements are often written with it, as we learn isotope notation later on. For example, carbon-14 is a carbon atom with a mass of 14. Uranium-235 is a uranium atom with a mass of 235. This mass number is the number of protons plus the number of neutrons. So when we write carbon-14, if you look on your periodic table, carbon has 6 protons. But this says carbon-14. That's because mass number is protons plus neutrons. So carbon-14 would have its 6 protons that make it carbon, and it would have 8 neutrons, leading to a mass of 14. And this is how much the nucleus weighs in AMU. Mass number is how much it weighs in atomic mass units. To determine the number of neutrons, all you have to do is subtract the atomic number. So in order to figure out that carbon-14 had 8 neutrons, I took my mass of 14, I subtracted it from my 6 protons that I know carbon has, and I got a total of 8 neutrons. Speaking of number of neutrons, we take our mass number and subtract our atomic number, just like we did on the previous slide. It has to be given. It is not on the periodic table. Can't emphasize this enough. The number of neutrons can change atom to atom. That's why it doesn't work to use the periodic table. The periodic table is static. It's just one square. But each atom can have a different number of neutrons, so we need to be given that mass number in order to do our calculation with it. An atom with a different number of neutrons is called an isotope. I recommend you highlight, star, underline that word. An atom with a different number of neutrons is called an isotope. Carbon-14 is an isotope of carbon. Carbon-12 is an isotope of carbon. They both have 6 protons. They both have an atomic number of 6, but a different number of neutrons. The number of electrons, in this case, is the atomic number if an atom is neutral. So we know, based on our CERs last week, that atoms overall tend to be neutral. So if we have a neutral atom, we know that if it has 8 protons, like in this oxygen, then it would also have 8 electrons because it needs to balance out. However, eventually we will get atoms that are no longer neutral. That's happening when they form compounds or we have something indicating that they have a charge. When they have a charge, they're called ions. But if an atom is neutral, it's the same as the atomic number. So here we're just drawing an atom. So we know that our protons and neutrons are found in the nucleus, and we know that our electrons are wandering around the outside. So I wanted to give you an example of what this looks like, and you should draw this entire example in your notebook because there will be many practices asking you to do this exact same thing. If you don't remember where this 14 or 6 came from, you might want to give yourself more information. We know that in order to find the number of neutrons, we take our mass number, which is written right there, and subtract it from our proton number, which is what makes carbon carbon. So I found this number on my periodic table. The part of an atom that's involved in nuclear changes, of course, is the nucleus. So we're going to focus on electrons a lot more later. For now, we're really going to focus on what's happening in that nucleus, especially when it's unstable. Isotopes. So what can change in the nucleus? What's happening there? Isotopes, reminder, are atoms of the same element with different amounts of neutrons. So for example, we could have magnesium with a mass of 24 AMU or a mass of 25 AMU. Magnesium will always have an atomic number 12 according to the periodic table, but the number of neutrons can change. So we want a way to write that out. And you can see here we have a hint of how we're going to be writing these things out. Both are magnesium, but it can have a different mass based on its number of neutrons. So isotope names and notation is how we write these out. So this right here should get copied and labeled. Both of these should get copied and labeled in your notes. We have our chemical symbol for magnesium, capital M, lowercase g. Capitalization is super critical when we're writing out elements. At the top, we have our superscript is mass number. That's our protons plus neutrons. That's the number that has to be given. And at the bottom, we have our atomic number, which is straight from the periodic table, magnesium 12. Our isotope name is just the element name with a dash and its mass number. So we know in this case we're not talking about magnesium 24, we're talking about magnesium 25 because our mass was given. And here's an example of different isotopes of hydrogen. So we have hydrogen 1 with a mass of 1. We know that that's mass because that's what our isotope notation states. Hydrogen 2 has a mass of 2. Hydrogen 3 has a mass of 3. So what does that look like? All of them are hydrogen, so they all have 1 proton. But they have different numbers of neutron, so their mass is different. So when we're drawing them out, you can see that as we go down here, we have 1 neutron added and 2 neutrons. And our symbols reflect that. So all of these have their 1 atomic number because it's hydrogen that can't change. But what changes is the mass number at the top. So we have a mass of 1, a mass of 2, or a mass of 3. I hope this video was helpful. Parts 3 and 4 are also linked in this NEO assignment and are available on Edpuzzle as well. And bring any questions that you have to class.